Yes.
Yes, I wanted to remind you about the issue of recording.
Yes, I'm doing that.
Okay, thanks.
All right. So first of all, if we look at a shunt machine, shunt motor, we know that the induced EMF is V minus IARA, and the field current is V over RF, and also that E is equal to a constant times the flux times the speed. And then we can change the formula like that. E1 over E2 is flux 1 N1 over flux 2 N2. But we know that flux is directly proportional to your field current, and therefore we can say that E1 over E2 is I field 1 N1 over I field 2 N2. That is known as the speed change formula. And then when we look at the torque, is equal to a constant times the flux times the armature current. And then we can do the same, T1 over T2, flux 1 I1 over flux 2 IA2. And since the flux is directly proportional to the field current, we can replace it like that. And that is known as the torque change formula. And there's just the compound motor. And then if we look at the series motor, we have that E1 over E2 is IA1N1 and IA2N2. And the torque is then IA1 squared over IA2 squared. Now, once we do the speed change formula, we put a diverter resistance in parallel with the field, and then that becomes the field current and the current through the diverter. And then we can say that the torque is T1 over T2 is IA1, I field 1 over IA2, I field 2. Now, I don't think you got this far in machines, but this semester we are going to do a lot of these type of problems where we change the speed of the different type of motors. So if we look at the first example, we have a 250 volt DC shunt motor as a shunt field resistance of 250 ohm and an armature resistance of 0.25 ohms. For a certain load torque, the motor speed was 1,500 revs per minute, taking an armature current of 20 amp. Now, if a resistor of 250 ohm is connected in series with the field, the load torque remaining the same, compute the new speed and the armature current. And we can assume the magnetizing curve is linear. So since the magnetizing curve is linear, it means that the flux is directly proportional to the field current. So N2 over N1 is E2, I shunt 1, or E1, I shunt 2. Yeah, I think that's right. Okay, yeah, let's change the speed now. So the field current is then 250 divided by 250, which is 1 amp. And then for the second field current, it will be V over R total, which is then 250 divided by 500, which gives us a half amp. And torque 2 is equal to the torque on the first one, because they said the torque was remaining the same. So we find that IF1, IA1 is equal to IA2, IF2. So IA1 is 20 divided by 0.5, which gives us 40 amps. armature resistance of 0.25. So we apply this formula, IA2 is equal to IA1 times IF2 divided by IF1. And that gives us 40 amps. And then E1 is V minus IARA. In the first case, it was 245 volt. In the second case, 250 minus 40 times 0.25. That gives us 240 volts. So N2 over 1500 is 245 over times 1 divided by 240 divided by 0.05. And then we get the speed is 2,930 revs per minute. Have you got that? If you look at this formula, then IA2 will be I field 1, IA1 over I field 2. So I field 1 was 0.5 times 20. And what was I field 2? 0.5. Oh, sorry. IF1, and that's 0.5. So that's where that comes from. 20 divided by 0.5. Are you all clear on this? Any questions so far? All right, let's look at another example. It says there, a 250 volt shunt motor has an armature resistance of 0.5 ohms and runs at 600 revs per minute on full load, taking an armature current of 20 amps. If a resistance of 1 ohm is placed in the armature circuit, compute the speed at full load torque and at half full load torque. So at full load, then we get 250 minus 20 times 0.5. That gives us 240 volts. Nothing is done to the field circuit because we just added a resistance in series there. So the field current is the same. So T2 is equal to T1. Therefore, IA2 is also 20 amps. And then E2 is V minus IA2 RA. And then remember, it's the 1 ohm resistance in series. So that becomes 1.5. And therefore, the induced EMF is 220 volts. So N2 over 600 is 220 over 240. And that gives us a speed of 550 revs per minute. Now, if the second torque is equal to half the torque, then IA2 will be 10 amps. And therefore, E2 will be 250 minus 10 times 1.5. That gives us 235 volts. So N2 over 600 is equal to 230 over 240. That gives us 587.5 revs per minute. Are you okay with that so far? I'm doing all the easy problems. You are going to do the tough ones. Okay. It says there, a 200 volt shunt motor has a field resistance of 40 ohm and an armature resistance of 0.02 ohms. It takes a current of 55 amp. Yes. Hello? Right, it runs at 595 revs per minute with a resistance of 0.58 ohm in the armature circuit. The torque remaining the same. What change should be made in the armature resistance to raise the speed to 630 revs per minute? So first of all, let's see. The shunt current is 200 divided by 40, which is 5 amp. And the armature current is 55 minus 5, that gives us 50 amps. And therefore, 0.58 plus the 0.02, that gives us 0.6 ohms. Therefore, E1 is 200 minus 50 times 0.6, which is 170 volts. Then we have the torque is the same. So IA1 flux 1 is IA2 flux 2. Because flux 1 is equal to flux 2, it means that IA1 is equal to IA2. So N2 over N1 is E2 over E1. And therefore E2 is N2 E1 over N1. That gives us 180 volts. So let R2 be the new value of the armature resistance to change the speed from 595 to 630. Then 180 is 200 minus 50 times R2. And then that gives us R2 is 0.4 ohm. So RA must be reduced to 0.04 ohms. So therefore we have to remove 2 ohms. 0.2 ohms. Then the second question, now suppose a 5 amp diverter is connected across the armature and the series resistance is adjusted that the motor speed again is 595 when the armature current is 50 amps. Compute the speed when the current falls to 15 amp again. So there we have IA1 is 50, IA2 is 15. So E1 was 170 and it was 595 revs per minute. So E2 is 200 minus 15.6 times 0.6, that gives us 191. And then N2 over N1 is E2 over E1. And then we get that N2 is 668.5 revs per minute. Now with an armature diverter, let's say let R be the new series resistance, then E2 is 200 minus IR minus 50 times 0.2. That gives us 199 minus IR. Since the speed is 595, E3 must now be 170 volts. So 170 is equal to 199 minus IR. And that means IR is 29 volts. So the PD across the resistance is 200 minus 29. That gives us 171 volt. And the diverter current is the voltage divided by the resistance. That gives us 34.2 amps. And therefore I is 50 plus 34, which gives us 34.2 amps. So if IR is 29, then R must be 29 divided by 84.2. That gives us 0.344 ohms. So if IA is equal to 15 amps, ID is I minus 15. 5 times IA minus 15 is 200 minus 0.334 I. And then we calculate IA, which is 51.46. And then E4 is 200 minus 0.344I minus 15 times 0.2. That gives the voltage of 182 volts. Then N4 over N1 is E4 over E1. And then we calculate N4 to be 637 revs per minute. Have you got that? All right, another example. Let's look at speed control of series motors. Now, can we change the speed of a series motor? We have a flux control method with field diverters, armature dividers, tapped field control, and paralleling field coils. Now, with field diverters, we get speed above base speed. Armature dividers, we get speed below base speed. And then a variable resistance in series with a motor. A two-pole series motor runs at 707 revs per minute when taking 100 amps at 85 volts. And with field coils in series, the resistance per field coil is 0.03, and that of the armature is 0.04 ohm. If the field coils are connected in parallel and the load torque remains constant, compute the speed and the additional resistors in series with the speed at 707 revs per minute. So the motor resistance will be 4 plus I would say if those two things are in parallel, they must be divided by 2, not 2 times. Why did they say that? Well, with the field coils in series, sorry. Then the motor resistance is 0.1 ohms, and E is 85 minus 100 times 0.1, which gives us 75 volts. Now with this series windings in parallel, the current through each one is half the armature current, and IA2 new is then IA2 over 2. Now with the torque the same, we can calculate that IA2 is equal to IA2 squared divided by 2. So 100 squared is IA2 squared over 2, and that means IA2 is 141.4 amps. And therefore, E2 is 85 minus, what is that, 141.4 times 0.04 plus 0.015. That gives us a voltage of 77.22 volts. And then N2 over 707 is 77.22 divided by 75 times 100 divided by 141.41 divided by 2. And that means our speed will now be 1029 revs per minute. Okay. Then if we look, DC series motor, having a resistance of 1 ohm, drives a fan with which the torque varies with the square of the speed. At 220 volt, the set runs at 300 revs per minute and takes 25 amps. The speed is to be raised to 500 revs per minute by increasing the voltage. Compute the voltage and the corresponding current, assuming the field is unsaturated. There we can say that since flux is directly proportional to the armature current, we get that the torque is directly proportional to the armature current. Therefore, torque is directly proportional to N squared. So IA squared is equal to N squared, or IA1 directly proportional to N1, and IA2 proportional is equal to N2. So IA2 over IA1 is N2 over N1. That means it's 500 over 350. And therefore IA2 is the 25 times 500 divided by 350. That gives us 35.714 amps. So E1 is 220 minus 25 times 1, which gives us 195 volts. And then E2 is V minus 35.714 times 1. Then flux 1 over flux 2 is 25 divided by 35.714. So that gives us 0.7, and therefore flux 1 is 0.7 flux 2. Now if we stick it into the formula of N2 over N1, is E2 flux 1 over E1 flux 2. We calculate V to be 433.7 volts. Okay, just keep calm. What about the second last question for tonight? All right, it says there, a 220 volt DC series motors takes 40 amps when running at 700 revs per minute. Compute the speed at which the motor will run and the current taken from the supply if the field is shunted by 0.1 ohm and load torque is increased by 50%. We have armature resistance is 0.15, RS is 0.1, and flux is directly proportional to the armature current. So again, we can say the torque is flux times IA. Oh, okay, we've got that. 9 minutes, okay. So T1 is directly proportional to IA1, which is 40 squared. So IA is the new current, only half IA2 will pass through the field. Torque 2 is flux 2 IA1, which is IA squared over 2. And T1 over T2 is IA2 over 2 times 40 squared. Because the field, the torque is increased by 50%. So 1.5 is IA2 squared over 3,200, which is 40 squared times 2. Then we get IA2 is 69.3 amps. So E1 is 220 minus 40 times 0.25, which is 210 volts. And E2 is 220 minus 69.3 times 0.2, which gives us 206.14. And then N2 over N1 is equal to E2 flux 1 over E1 flux 2. And if we substitute it in there, we get that N2 is 794 revs per minute. And our final problem for the night. A 200 volt DC series motor runs at 500 revs per minute when taking a current of 25 amps, where RA is 0.2, RS is 0.6. Compute the speed when a diverter of 10 ohm is connected across the ohmmeter. Assume no magnetic saturation occurs. So E1 is 200 minus 25 times 0.8 is 180 volts. I2 is the new current. So VRS, that is 0.6 times I2, which is that. That's the theory. So VB is 200 minus 0.6 times IA2. ID, the diverter current, is then that voltage 200 minus 0.6 I2 divided by 10. And that gives us IA2 is I2 minus 200 minus 0.6 IA2 divided by 10. And then if we go crazy and we substitute and everything there, then we get that 10 IA2 is equal to 10 I2 minus 200 plus 0.6 I2. IA2 is then 10.6 I2 minus 200 divided by 10. And because the flux, the torque, is directly proportional, we get that flux 1 I1 is flux 2 I. So 25 squared is equal to I2 times 10.6 blah, blah, blah. And we multiply and divide and go mad. And we get I2 is 35.6 amps. So VB will be 200 minus 35.6 times 0.6, which is 178.6 volts. Then we can calculate IA2, which is 17.74 amps. And then E2 is 178.6 minus 70.74 times 0.2, which gives us 175 volts. And again, our formula N2 over N1 is equal to E2 flux 1 over E1 flux 2. And if we substitute the values in there, we find that N2 is 314 revs per minute. Now, I hope this will give you some idea of the problems that will be coming. And that is in chapter, what was it, on motor speed control? In my old book, it's chapter 30. I can't remember what's it in yours. Let me quickly check. Well, it will be those motor problems. No, I can't. I think it's 46. No. Then it must be 49. If it's not 49, it's 50. Damn. If it's not 50, then we've got a problem. No. There's the one motor problem. Come on, open. Yeah. There's that. It's also 30. So you must do all of them. You can see there's quite a lot of them. But we've got about 2 weeks to cover all of this. So hopefully you will work through the problems. And when do I see you again? Tuesday?
Sir.
Yes.
So for some of us, this is the first class. So are we supposed to do chapter 30 only for now?
No, the first chapter was the, on energy management, the slides that I sent you.
Oh, okay.
Right. And this is then chapter 2. But yeah, you can read through those stuff. I'll tell you what to study later on. But in the meantime,
All right.
read through it and then start working with this problems. So, do I see you Tuesday night?
Yes, sir.
So we'll make it
Yes, sir.
Tuesdays and Thursdays.
Yes, it will work that way.
Okay, good luck then. If you've got a problem, you can WhatsApp me or email me, and I'll try and help you before the class. All right.
Okay.
Okay,
All
guys.
right. Thank you.
I'll send you the link the moment that this thing is finished.
All right.
Okay, sir.
Yes.
Sir, can you please send us the slides on WhatsApp? The slides that we're doing today.
You already have it. Just ask who's the study leader, Warren? Who set up the group?